Okay, so our today's lecture starts from the basic rocket equation that we call Tsiolkovsky equation, and we try to define some fundamental rocket performance terms. So that is our beginning of today's lecture. So derivation of rocket equation is one of the part of today's lectures, which is based on Newton's law, the fundamental definition of parameters, which are very important in rocket propulsion and the design of rocket propulsion system. The basic relation of propulsive forces, exhaust velocity, and other parameters like efficiency related to creating and converting energy. So these things are going to be discussed. So let's start from a simple Newton's third law, that is the law of reaction and action and reaction. So whenever there is an action force on an object, there is an resistance force that encounter back. So that is action and reaction force. So based on that concept, the Russian scientist in early 19th, he was Tsiolkovsky. He focused on the dynamics of vehicle. Okay, the mass of which is decreasing as the jet of matter is projected rewarding. Means what? His intention is when there is an increasing velocity is accompanied with a decreasing mass. In the case of this rocket propulsion, the basic concept is the total mass of the whole propellant decreasing from time to time, and the rocket velocity increasing from time to time. So that is a decreasing mass accompanied with increasing velocity, which happened because of the ejection of the jet matter, which is both gases which are ejected in the rearward of the vehicle. Okay, so the force that produces exhaust is the same force that propels the rocket. That propels the rocket means the thrust. Okay, so that is the point where Tsiolkovsky started to discuss the possibility of rocket propulsion. Means sending some object to space can be achieved. He believed on this issue. Okay, so that is based on the Newton's third law. That Newton's third law, actually this is Newton's second law, that momentum conservation, that force is equals to the change in momentum to time. Okay, d mv dt, which is m dot ve. So m dot means the mass flow rate, and v is the effective exist velocity or effective velocity. Okay, so this is the beginning of the equation. So in this equation, the thrust of the rocket is expressed in terms of mass flow rate. Okay, so this is thrust, and this is the mass flow rate. Okay, and the effective exhaust velocity is here. But this is not the only thrust. There is also another thrust we call pressure thrust. This is just momentum thrust. We call this as a momentum thrust. That is a very big value. That's why we give emphasis on momentum thrust. But the pressure thrust depends on our nozzle design, so that we'll see that in the next discussion. So when we are going for Tsiolkovsky's rocket equation, the principle is what we have discussed right now. Okay, here we deal with the case where the mass of object is changing. The mass is continuously changing. Why mass is changing? A massive ejected gas comes out through the nozzle due to the combustion of the propellant inside the combustion chamber. So the propellant is consuming from time to time. That propellant consumption is accompanied with the acceleration of the change in velocity. Okay, so the mass is changing from time to time. So for such case, we analyze the motion of rocket, which changes its velocity by ejecting burned fuel gas. That causes the acceleration in opposite direction. Okay, so the acceleration of the rocket in opposite direction. That means, let's see. So this is the acceleration of rocket direction, and massive ejection of hot gas are through the nozzle of rocket here. Okay, so we call this as the thrust, and this as the uh, um, ejected gases, and there is a momentum will occur in between. So this is the way. Specifically, a fully fueled rocket. Look, a fully fueled rocket in deep space has a total mass m. If we consider some total mass m, means most of the time this m mass m naught we call. Why it is m naught? Initial mass. Okay, that is initial mass of fuel and the rocket. It contains mass of fuel and mass of rocket. M naught is the sum of mass of fuel and mass of rocket. At the same moment in time, the rocket velocity v and the mass m. This means this is the combination of the mass of empty rocket. So I called it as mass of rocket. The empty casing simply without any propellant, it is mass of rocket only. That means structural mass, payload mass, other mass are also there. This electronics, navigation systems, and other things, those masses are other mass. So the big mass or the maximum mass in the rocket system is most of the about 98% of the rocket is the fuel mass. Okay, so it is a combination of empty rocket and the mass of remaining unburned fuel. Means after some times, initially full of the mass called initial mass. Then once it starts burning, some of the mass is decreasing by imparting some velocity gain. Velocity gain is there, mass decrease is there. So then after there is a change. So let's see what are those things. This is the concept behind of it. So this is initial mass of fuel and the mass of rocket together. And at initial time, velocity v only. But after sometimes, after some mass is burned out and ejected through the nozzle, we can have v plus delta v. Means this is the at the moment the rocket ejected some mass, and then we have here delta ve, means change in mass of propellant, and delta m. Now this is the amount of consumed propellant mass. Okay, this delta m means consumed propellant mass. Okay, and here mass is decreasing, velocity is increasing. Okay, so this mass now is initial mass minus ejected mass. So that is the point where the derivation starts. Okay, so at time t0, the rocket total mass m is equal to mr plus mf, where mr is the mass of empty rocket and the mf is the mass of the fuel. And the entire system moving at a velocity of v. Okay, that is velocity v. Now, when we come to initial momentum, momentum at initial is equal to mv, which is mr plus delta mf times velocity. This is the initial momentum. And the final momentum is, this is initial momentum, P initial is here, P initial, and P final is here. So the final momentum is equal to mr times v plus delta v. Look, this is mr now. This one is mr times b plus delta b, and plus this ejected mass velocity, which is delta b of the fuel or at the exit times velocity of exit velocity. So now, based on the momentum conservation principle, initial momentum is equals to final momentum, or we call final momentum minus initial momentum is equal to 0. That is called the momentum conservation. So from that, finally, what we can get, mr delta b plus delta mf ve minus delta mf v. So here this subscript indicates R for stands for rocket, F stands for fuel. Okay, so don't forget this thing. Now, considering the relative velocity at the exit, the relative velocity at the exit, which is equals to v minus v exit, u is equals to b minus b exit. So this u is the relative velocity at the exit. Okay, exit relative velocity. So we substitute instead of VE, because here we have delta V, V terms. So we have two different terms. So to remove this one, we use VE is equals to V minus U. So when we substitute this, finally we can get this equation. So what is the, in this equation, we can see delta mf, okay? mr, mass of rocket, change in velocity, minus change in mass of fuel, times the relative velocity, which is equal to 0. Now the mass flow rate or the mass of propellant is continuously changing. That the change is negative change. It decreases from time to time, so that delta mf is equals to considering to the limit of derivative minus dmf. That's minus indicates that the continuous change is the negative change, means continuously decreasing. Okay, so let's substitute this one instead of delta mf in the previous equation. So we have mr dv, means delta v is equals to dv, this dv, and delta mf is equals to, again, minus d mf. Yeah. By doing that, we have this equation. Okay. So, which means dv is equals to u dmf over mr, which is equals to 0. That gives us dv is equals to minus of u dmf over mr. So, hello? Hello?
I think I start.
Any when the yes, የተደማመጥን ነው?
ግን የሆነ ድምፅ አለ እንትን መሀል ላይ የሚገባ መሀል ላይ የሚገባ የሆነ ድምፅ አለ ሲጢጥ ሲጢጥ የሚል እንደሆነ
እኮ እሱ እኮ ነው፣ ለዛ ነው የጠየኳችሁ። ኦኬ አሁንስ እንትን ይላል?
አሁን ኖርማል።
ኦኬ ኦኬ። So the final equation is dv is equals to minus u dmf over mr. The mass of rocket here we consider, but the continuous change of velocity, the continuous change of mass is the mass of fuel, so that we consider the fuel mass rather. Okay, this can be as it, but we consider the fuel mass, that the rocket mass change is accompanied by fuel mass only. So then by integrating this equation, we can get change in velocity v final minus v initial, which is equals to u ln of fuel mass initial final mass. Now this is not fuel mass, final mass to initial mass. Final mass means the remaining fuel content, the fuel content after some times. Okay, so minus u, the relative velocity, exit velocity, minus u times ln of mf minus ln of mi. So this I is initial, this I is final, not fuel but final and initial. እዚህ ጋር እንዳይምታታባችሁ ኤፍ እዚህ ጋር ፋይናል ለማለት ነው። አይ ኢኒሻል ነው፣ ችግር የለም፣ እሱን ትረዳላችሁ። ሶ ይሄ ኢኩዌሽን ይመጣልናል ማለት ነው። ሶ ዲስ ኢኩዌሽን ኢዝ ኢኳልስ ቱ we can it is ln of mf over mi. So if you reverse this thing up and down, means initial mass over final mass, then the negative sign will be changed. This negative sign in front of you will be changed to positive here. So delta v is equals to u ln of mi over mf. So mi is the initial mass before the rocket launch, and mf is the final mass after some amount of the mass of, sometimes even the complete propellant may be burned. So this equation is called the rocket equation, and it is called the Tsiolkovsky rocket equation. So when we consider some gravitational attraction, means if our rocket is in the gravitational field, then there is some reduction in the velocity happen because of the gravitational dragging. የሚረብሽ ነገር አለ? ሄሎ
የሚረብሽ ነገር
ምን?
አይ ቲንክ አይ አብዱ ገና መግባቱ ነው እና ሚውት ስላላረጋው ነበር።
ኦኬ ኦኬ እሺ፣ አሁንስ ሚውት አደረገው?
አሁን የሁሉም ሚውት ሆኗል።
ኦኬ ኦኬ። So when it is in the gravitational field, it becomes g delta t. This is the amount of because of the gravitational drag, there is some amount of velocity be decreasing, velocity decrement. So delta v is equals to this is in regardless of the gravitational attraction. Okay, so when we consider gravity, we have this amount g delta t minus g delta t is another part. So we'll see what this ISP and the other thing. So it can be expressed in terms of ISP, G naught ISP ln of mf minus t, because G comes out here, T is alone here. Okay, so this is the expression for rocket equation. Now let's come to the basic definitions and terms which are very important in our rocket design. The first term is the thrust. So thrust is one of important part of the rocket propulsion. So rocket thrust is generated by exchange of momentum between the exhaust and the vehicle, and by pressure imbalance at the nozzle exit. So from that definition, we have two components of thrust. One is the momentum thrust, that is this one, which is m delta v, and another is the pressure thrust. So we'll see pressure thrust in the next. So this is the momentum thrust. So as you see from here, Fm indicates momentum thrust. M dot is the mass flow rate of the propellant. V is average exit velocity. V naught is initial velocity. Okay. So finally we have this equation. So we can represent it in terms of weight. So this is weight. Mass weight is equals to mass times gravity. So mass times gravity. From that point, mass is equals to weight over gravity. So whatever we are considering here is the constant gravity at the Earth's surface, just at the Earth's surface only. There is a variable gravitational field that is not considered here. Okay, so this is weight of propellant divided by G naught times VE. So VE is the exit velocity. Okay, so by considering the initial velocity of the gas at 0, that V naught is equals to 0. So the above this equation becomes this. This is called the momentum thrust. Okay, in most cases, actually we use 9.81, not 0.1, but 9.81 here in most cases. For our calculation, for our convenience, the value is 0.866 like that. So we use 9.81. Or if someone wants to, I don't like this inch system or feet system. If someone wants, it's 32.174 feet per second square. And this is 9.81 meter per second square. The next is the pressure thrust. So the pressure thrust is developed because of the pressure difference between outside and the inside. As we see here, this is the pressure inside the combustion chamber. When the fuel is burning inside the combustion chamber, high pressure developed here. But this pressure is divided into axial and the radial direction. Some of them are acting in the radial for direction. Some of them are acting in the axial direction. So the one which accompanying axial direction has an effect for our pressure thrust. Okay, so we decompose the pressure vector. Every pressure here, every point, in every point, this pressure will be resolved into normal direction. Here there is normal component, and there is radial component. Internet connection loose ሳይሆን አልቀረም። እየሰማችሁኝ ነው?
ይሰማናል። ይሰማናል።
ኢንተርኔት እኔ ጋር ሉዝ እያለኝ ነው። ኢንተርኔቱን ኮኔክት አድርጌ ልመለስ።
እሺ
አንዴ ከወጣ ችግር ነው። Yeah, let me try. So pressure በሪዞልቭ በማድረግ በኤክስ እና ዋይ ዳይሬክሽን ሪዞልቭ በማድረግ axial direction means በእኛ ጊዜ ኤክስ ብንለው the x components have an effect in our pressure thrust. Okay. So by resolving summation of force in the radial axial direction is equal to pressure thrust. So pressure thrust is equals to P exit pressure times exit area. E represents in most of our discussion, E represents exit. Okay, C represents combustion chamber. T represents throat. Okay, so that PEAE means exit pressure times area exit area. So pressure thrust in the ambient pressure is not zero because there are some atmospheric pressure. This formula works. The formula 3 works only as when ambient pressure is zero. but in the atmospheric area, this is not the correct way. So that it is P exit minus P atmosphere or ambient pressure times area exit. So this is the pressure component of the thrust. So summing up the two components, the momentum thrust plus the pressure thrust gives us the total thrust. Okay, so this is the thrust equation in our case. So this is general thrust equation. It is, instead of, you can put it mass flow rate of propellant times velocity exit. Effective velocity. This is not exit velocity, but effective velocity. We will see some other velocity component also. So this is effective velocity. So this is some explanation on the two components of the momentum thrust and the pressure thrust. So the first term is called the momentum thrust, which is given by the product of propellant mass flow rate. Look, mass flow rate, the product of mass flow rate, and it is exhaust velocity relative to vehicle. Okay. And the second term is pressure thrust, which consists of the product of cross-sectional area at the nozzle exit. Cross-sectional area at the nozzle exit, and the difference between the gas pressure at the exit and the ambient pressure. So this is the definition. Okay, when the exit gas pressure is less than the surrounding fluid pressure, the pressure thrust is negative. So that negative surrounding pressure thrust is not required. You see, if this is negative, means it is decreasing our total thrust. Otherwise, we need this part. This part can be sometimes negative, sometimes zero, sometimes positive. We can discuss what is positive, what is negative, what is zero. If this term is zero, that means PE minus PA is equals to zero, means we are considering it as optimum expansion of the nozzle. Okay, optimum expansion of the nozzle. If this term is minus or negative, then it is called under expanded nozzle. Under expanded nozzle is not good because it reduces our thrust. Our intention is to gain more and more thrust. Okay, so that thrust should not be reduced. So zero, negative, and plus condition is there. Plus condition means P exit greater than P atmosphere, then we can get positive value from here, which gains the thrust. It gives positive thrust, so that then the nozzle is called over-expanded nozzle. The nozzle of the rocket is called over-expanded nozzle for the positive case. This is optimal. Sila nozzle senumar ይሄን ፓርት ኦፕቲማል ይሄን ፓርት እንደገና ዲስከስ እናደርጋለን። ስለዚህ አሁን ሲምፕሊ እዚህ ቶፒክ ላይ ኔጌቲቭ ሚንስ under expanded, under, and plus means over expanded, over. So these three conditions will happen in the case of this thing. So when the ambient pressure equals the exit pressure, that means PE minus P is equal to zero, then the thrust equation is this one, because this part is fully zero. So this is the case of optimal expansion. in the vacuum of space, P atmosphere is equals to 0. In the vacuum, that is the maximum thrust condition. The maximum thrust condition is the condition where P atmosphere is equal to 0. So we design our rocket for the maximum atmospheric condition. So that case, this part PA0 means we have PE, AE only. So that our thrust equation is this one. This equation is the maximum thrust condition. Okay, so these are the design consideration. Okay, most nozzle have area ratio that is known as exit area to throat area ratio, which is designed so that their exit pressure will equal to surrounding air pressure. Look, this is called optimum design. Okay, optimum nozzle design, or the expansion of the nozzle is called optimum expansion ratio. So equation 5 in our case means this equation shows the thrust is independent of rocket unit's flight velocity because change in P affect, this atmospheric pressure change affects our pressure thrust components. Okay, so the change in atmosphere have a noticeable effect in our calculation. Another one is effective exhaust velocity. That effective exhaust velocity in actual rocket nozzle, the exit velocity is not uniform. It is varying because of various parameters over the entire cross-sectional area of the. So uniform axial velocity C, this is called effective exit, assumed for all calculation. So that we call it as the effective exhaust velocity, which is the average of mass equivalent velocity. So it is force divided by mass flow rate. C is equals to force over mass flow rate. Or we know this thrust force, this force is thrust, okay? So which is equal to 1 over m dot as a whole. This is the thrust equation we have from the previous calculation. So and then finally we can get C is equals to VE plus PE minus PA times area exit over mass flow rate. So if this part is 0, this is directly VE only. C is equals to VE in the optimal expansion case, okay, which is equals to G naught times ISP. This ISP still we didn't discuss. We will discuss it in the next. Characteristic velocity or C star. Please don't forget this thing. Effective exit velocity C, characteristic velocity C star. This has meaningful terms in rocket calculation, so that don't forget. Okay, so this is C star, which is given in equation P in the combustion chamber, pressure at the combustion chamber divided times area at the throat times G naught over weight flow rate, which means when I bring this G naught here, it becomes MP. So PC80 over MP dot. This is called characteristic velocity. So the characteristic velocity is not physical velocity. It is not exactly physical velocity, but it is used for comparing the relative performance of chemical rocket propulsion. So we check our rocket performance, especially using there is bomb burning test or ballistic burning test methods in the rocket testing. We check the specific characteristic velocity first. That helps us to determine the rocket performance. Okay, so so C star is independent of nozzle characteristic. This is independent of nozzle characteristic, but it relates the efficiency of the combustion process. So the specific impulse ISP and the effective exit velocity C